bird. It's a plane. No, it's someone with curls. It's Math Girl. Alright, we're doing double angle identity. So looking at 12D5, this says to derive sine of 2a using the sum identity. So we need to use the sum identity of sine, and we're going to get this sine 2a. First off, let me write the formula for the double angle identity for sine. Here's what we're going to derive. Sine of 2a, and what that means is 2 times an angle. Sine of 2 times an angle, that is the same as 2 times sine of that same angle times cosine of the same angle. Don't forget, when you see sine and cosine next to each other, that implies multiplication. 2 times sine of a times cosine of a. So sine of 2 times of an angle is the same thing as this. We're actually going to derive this formula using the sum identity. And again, why do we do this? Because a long time ago, when NASA was sending people to the moon, they didn't have nice little computers in their hand like we do today. And they would have to use formulas like this. So, going back to the sum identity of sine, okay? So the sum identity for sine is sine of a plus b equals sine of a times cosine of b plus cosine of a times sine of b. Well, what if both of these were the same angle? The fact that one is a and one is b implies that they're two different angles. Like that could be 30 degrees and that could be 45 degrees. Okay, what if they were both 30 degrees? So in other words, what if they were both the same angle? If they were both the same angle, then we would have sine of a plus a, if they're both the same. Well, from algebra, what is a plus a? One of these plus one of these is two of these. 1a plus 1a is 2a. So now we have sine of 2a. Well, that's the left side of our double angle identity, okay? So going back to the sum identity, if they're both a's, then here, everywhere we see an A, we're going to replace it, like going back to the sum identity. Everywhere we see an A, we're going to replace it with A. Everywhere we see a B, we're going to replace it with A. So in other words, over here on the right, we should have all A's. So using this formula of sum identity, then you have sine of A, cosine, everywhere I see a B, I'm replacing it with A, plus cosine of A, everywhere I see a B, I'm replacing it with A. Okay? Sine A, cosine A. Cosine A, sine A. Are those the same kind? Because here, can I rewrite this one to say sine A times cosine A? Is cosine A times sine A the same thing as sine A times cosine A? Yes. Is xy the same thing as yx? Yes, because multiplication is commutative. You can switch them around the operation sign and they're still the same. 4 times 5 is the same thing as 5 times 4. So we can switch them around. So we have, essentially our coefficient in front is 1. They're the same kind. Sine A, cosine A. Sine A, cosine A. One of these plus one of these is 2 of these, and your these does not change. And so we just use the sum identity for sine, and proved that that sine of 2a, which is called the double angle identity, is equal to that. Okay, now let's look at 12b number 8. We're basically going to be using these double angle identities to verify and prove this. Okay, so the instructions on this was to verify. We're going to verify that this equation is true. And do you notice this is a double angle identity. 2 times an angle. Anytime you have 2 times in front of your angle, that is double angle identity. So we're using cosine. So let's look at the formula for cosine for double angle identity. You notice that there are 3 of them. Okay? Do you notice that this is just one of the formulas for cosine, for double angle identity for cosine? Okay? So all we're doing is we're verifying these, and It's okay if you just want to use decimals. It doesn't tell you whether or not to use ratios, to use fractions, or to use decimals. So we're just going to use decimals. So here, 2 times 20 degrees, that would be 40 degrees. So we're going to see if cosine of 40 degrees is equal to all of this. We're proving that these double angle identities work. Okay? Just as a reminder that cosine squared of 20 degrees means cosine of 20 degrees and then you square it. But our trig functions, the square is written in between your trig function word and your angle. So this also means sine of 20 degrees, then square it. Okay? So cosine of 40 is 0.7660. Cosine of 20, 0.9397. Then we're squaring it. Sine of 20, 0.3420. Then we're squaring it. So we already know the left side equals this. So 0.9397, squaring it. Hang on, I didn't hit my right button. 0.9397 is 0.8830. Now squaring 0.3420. 0.11. Well, that comes out to 696. So we're going to make it 0.1170 to round to 4 decimal places. So subtracting the 2 does come out to 0.7660. Sometimes on these, when you're verifying, sometimes that last decimal could be off a little bit, and that's due to rounding. So basically we showed that this double angle identity proves that it's a true statement, that these double angle identities do work. Okay, now we're looking at 12C number 6, and on this one it says to use ratios. Ratio is a fancy word for fractions. We use a fraction value, which may have a radical in it, to evaluate tangent of 2 theta. And in this case, theta is going to be 60 degrees. So basically we're evaluating tangent of 2 times 60 degrees. Double angle identity. Okay? That's what they're wanting us to determine, evaluate this double angle identity. Don't just say 2 times 60 is 120 and then tangent of 120. That's not what they're wanting us to do. They want us to use the formula for double angle identity for tangent. Okay, so for tangent, there's only one formula for double angle identity for tangent. Its tangent of 2A is 2 times tangent of the angle over 1 minus tangent squared of the angle. One thing I want to point out, this 2 is in front of the angle. This means 2 times the angle. This 2 is a coefficient in front of it. So this is tangent of the angle. So you do tangent of the angle, then do 2 times it. This is 2 times the angle, then do tangent of it. These 2's, you have to watch out for these 2's. Don't confuse them. This one's a coefficient. This is double angle. Okay? So we're going to use this formula with our theta or our A being 60 degrees. So we're going to use this formula, but everywhere we see an A, we're replacing it with 60 degrees. It's like this is our A right there. So we're taking the formula, 2 times tangent of 60 degrees. Everywhere we see an A in the formula, we're replacing it with 60 degrees. 1 minus tangent squared of 60 degrees. Okay, just as a reminder, that means tangent of 60 degrees, then square it. And they're wanting us to use ratios, fractions, or radicals. So 60 degrees, special angle. So 2 times tangent of 60 degrees from your formula sheet, or if you haven't memorized, tangent of 60 degrees, square root of 3. All over 1 minus tangent of 60 degrees, I just told you, square root of 3, square it. Okay, 2 times square root of 3 is just 2 square root of 3. 1 minus square root of 3 squared. That's the same thing as square root of 3 times square root of 3. Square root of 3 times square root of 3 is square root of 9, which is just 3. So, and then in your numerator, 2 square root of 3, 1 minus 3, watch your signs, negative 2. So now we're down to rules of radicals. Radicals to radicals, whole numbers to whole numbers, so that you can reduce this right there. 2 divided by negative 2 is a negative 1. And I'm not going to write my negative 1. It's not wrong. You can write your negative 1 there, or you can just have negative. So basically what we evaluated, or we found the answer, that tangent of double angle 2 times 60 degrees is negative square root of 3. You can even put that in your calculator to say tangent of 120 degrees, you can get a decimal, and that should be the same decimal as negative square root of 3. Okay, this is another type of problem that you will encounter when doing double angle identities in 12b11. They're asking you to find sine of 2 theta and cosine of 2 theta. You need to really watch for this. This is double angle identity. Double angle identity. Okay, and they're giving you that sine of theta is 3/5, and they're telling you it's in the first quadrant. When they tell you in the first quadrant, you should be jumping for joy because that's the positive world. Everything is positive in quadrant 1. Okay, sine theta equals 3/5. What does sine mean? Sine theta. Sine is opposite over hypotenuse. So when they tell you that sine theta is some fraction, I would always recommend drawing you a picture. Okay, we use these trig functions when we have a right triangle. You can pick where you want theta, so I'm going to pick theta to be there. So therefore, if I know that sine theta is 3/5, opposite over hypotenuse, if I'm standing here, that means 3 is right there. And then hypotenuse is 5. So I can draw me a picture. So can I find this other side? Because then they're asking us to find sine 2 theta and cosine 2 theta. Well, since I'm dealing with cosine, cosine is adjacent over hypotenuse. If I'm standing here, this is my adjacent side. So I know I'm going to have the adjacent side. How do I find the third side of a right triangle? Pythagorean theorem. Okay, so I know I'm going to need to use Pythagorean theorem. Remember, this is hypotenuse. So Pythagorean theorem, leg squared plus leg squared equals hypotenuse squared. I know one of my legs. I don't know the other leg. I know the hypotenuse. 9 plus leg squared equals 25. Subtract your 9 to the other side. Leg squared equals 16. To find the leg, take the square root of both sides. So now we know that leg is 4. Okay, so that side is 4. You should be able to go through that pretty quick now. Okay, now that we know all sides of our triangle, they already told us that sine theta is 3/5. So now I should be able to find cosine theta. Cosine theta, standing at that angle, cosine is adjacent over hypotenuse. This is my adjacent side. So cosine theta is 4/5. Why do I need those? Because I need to find sine of the double angle and cosine of the double angle. So go to your formula for sine of double angle. I have it written right there. Okay, so sine of my double angle is 2 times sine of my angle, cosine of my angle. In this case, we're using theta. So I can replace all of these with theta. Okay, so sine of 2 theta, that's what I'm finding. Okay, equals 2 times sine of theta, I have it right here. Sine of theta is 3/5. Cosine theta, oh, I just wrote it right there. 4/5. Multiplying fractions, turn this into a fraction if that makes you feel better so you can visually see it. How do you multiply fractions? You multiply everything straight across. 2 times 3 times 4. 2 times 3 is 6. 6 times 4, 24. 1 times 5 times 5, 25. Can't reduce that. Always reduce if you can. So, what we calculated, or what we discovered, I like calculated, was that sine of the double angle, sine of 2 theta, is 24/25. Okay, now we need to do cosine double angle. So you can pick whatever formula. There are 3 formulas for cosine. I used this one. 2 times cosine squared of A minus 1. Everywhere we see an A, instead of using A, in this case, we're using theta. So cosine of 2 theta, that's what we're trying to find. This, and remember, this means that. Okay, well, we know what cosine theta is. We already did that one by drawing our triangle. So that was 2 times cosine theta was 4/5. We need to square that, minus 1. Do your order of operations. PEMDAS says we do exponents first. That's the same thing as saying 4/5 times 4/5. So that would be 2 times 16 over 25. 16 over 25 is 4/5 times 4/5. Minus 1. Make this into a fraction. Multiplying your fractions. 2 times 16. 32 over 25 minus 1. You're subtracting fractions. Now you have to do a common denominator. Okay? I need here to be a denominator of 25. Right now I've got 1 over 1. Multiplying it by 25, then I basically end up with 25 over 25. So now all you have to do is subtract your numerator. So 32 minus 25 is 7. So that would be 7/25. You can't reduce that, so that would be your final answer. So let me just summarize what I did in this problem. They gave you sine of 3/5. Sine theta is 3/5. From this point, draw you a triangle because sine is opposite over hypotenuse. Draw a triangle. Find your third side because then you can do cosine. Once you have your sine and your cosine of your triangle, then you can now take these numbers and plug them into your double angle identity formulas to be able to find the double angle identity for each one of those. Okay, where else can you see double angle identities? In proofs. I know you're all jumping for joy. So we're looking at 12b13. Here we are proving, basically same thing as verifying, you're proving that the left side equals the right side. 1 plus cosine of 2 alpha equals 2 times cosine alpha squared. Okay? This is double angle identity. This is a coefficient in front of your trig function. Don't get the two places confused. When your number is in front of your angle, that's double angle identity. When your number is in front of the trig function, that is a coefficient. Okay? So here, when you come across a double angle identity, you can replace it with one of your formulas. Okay? I'm going to choose to use, cosine has 3, but I'm going to choose to use, if I said this, I'm just going to write this off to the top side. Cosine of 2 alpha equals cosine squared alpha minus sine squared alpha. That is one of your double angle identity formulas. So I am replacing this with all of that right there. Okay, so that would be 1 plus cosine squared alpha minus sine squared alpha. Okay? Now, I haven't worked this out ahead of time, so you guys get to see me think out loud just as you were working it. So, remember I'm trying to get the left side to equal the right side. And you can change both sides. I'm going to change this because anytime that I see a cosine squared, when I see squared, then I'm usually thinking of Pythagorean theorem in trig notation. Okay? So, since over here I have some cosine squares and some sine squares, here I have a cosine squared, so I might not need to change it, I might need to change it. Don't know yet. So, all I'm just trying to get you to think of is anytime I see cosine squares and sine squares, I always think of Pythagorean theorem and trig notation. Okay? So, for now, let's see, I'm going to leave this, I'm not going to change it, I'm going to leave it like that for now. So, I have a cosine squared over here, but I also have a sine squared. And on the right hand side, I don't have any sine squareds. I only have cosines. So, on the left, can I change my sine into cosines? Okay, so if you look at in your Pythagorean theorem and trig notation, that if you look at sine squared, okay, sure, you can change that into something else, but if you rearrange, something I want you to learn how to look for, I have a 1 here, and then I have a negative in front of sine. What if I rearrange this to say cosine squared? I'm just looking at my formula sheet and seeing what I can do. I'm just trying to think ahead like chess. Plus 1, because that 1 is positive, minus sine squared alpha. Okay, now look at this. And look at your formula sheet. Can you change 1 minus sine squared alpha into something else? Yes. 1 minus sine squared alpha actually equals cosine squared. So here we still have this cosine squared. But looking at your formula sheet, this whole thing actually also equals cosine squared. Okay, so now I've got one of these plus one of these is 2 of these. And remember, with proofs, there could be more than one way to work this. I know that there is another way to work this other than the way that I did it. I could go work it a different way and probably put everything in sine and come out to where the left side equals the right side. So if you didn't work it the same way, don't panic.